So in this video is going to review some derivative techniques from limit process through the chain rule, including some trig derivatives, product rule, quotient rule, no exponential or logarithmic in this bit. Also, I got one implicit differentiation example. All right, let's take a look. By the limit process, so the limit process, or the definition of derivative, is f prime is the limit as delta x, or h. I'll use h just because it's a little easier to write. F of x plus h minus f of x over h. Okay, so what I like to do is just kind of find out what f of x plus h is. Just do a little bit of algebra over here, and then I'll rewrite the whole derivative, because that sometimes can get a little messy. F of x plus h means I plug in x plus h everywhere I see an x in my function f. So that means x plus h squared plus x plus h minus 2. You've probably squared this guy out a couple times. That's x plus h times x plus h, which means you got a FOIL. So you should get x squared plus 2xh plus h squared plus x plus h minus 2. Okay, so that means my derivative is the limit as h goes to 0 of f of x plus h, which is that guy, x squared plus 2xh plus h squared plus x plus h minus 2. That is f of x plus h minus f of x all over h. Now be careful that we're gonna subtract f of x. That means the signs, when I distribute that negative, the signs are gonna change for all of those. So let's see if we can save a little bit of work. X squared minus x squared is 0. Positive x minus x is what that'll be. That's 0. And then negative 2 plus 2, right? Minus negative 2, that's 0. So those 6 terms are now gone because 3 cancel with 3. So we haven't taken the limit yet, so I still have to rewrite limit. 2xh plus h squared plus h, and that's all gone, all divided by h. Okay, and the goal is, you can see we can now simplify this fraction by dividing h into all 3 of these terms. Now that there's an h in all terms in the numerator, I can take this h into each one. Or another algebraic option to see would be to factor out the h and then cancel the h's. It's the same thing. So that would leave me with, it's equivalent to 2x plus h squared over h is h, and h divided by h is 1. And now, and only now, can I take the limit as h goes to 0 by plugging in 0 for h, and it leaves me with the derivative, which, by the way, you should know if you've gone on to study the derivative rules. You can get to here really quickly. From here to here, you can get really quickly by using your derivative rules. 2x plus 1. All right, speaking of derivative rules, find the derivative of the function. You study the quotient rule, but I want to avoid the quotient rule if I can, right? In this case, if I can just do a little bit of algebra, if I'm dividing this trinomial by a binomial, much like we did in the last example, I can just divide each term, since there's just that one x squared in the bottom. This function is the same as x to the first minus 2x, minus 2, x squared over x squared is 1, plus, and I want to rewrite this with using negative exponents so I can take the derivative using that power rule. So 7 divided by x squared is 7x to the negative 2. That's f. We didn't do any calculus yet. Don't give me, that's not your answer. That's just f. Now f prime is the derivative of this. Okay, so that's 1 minus 0, derivative constant is 0, and this would be, use your power rule, minus 14x to the negative 3. And the question is, how do we write that? Well, at least write it without your negative exponent, and I'd be okay with that. A textbook would probably want you to do one of these guys. It's a 3. Okay, but this is fine. I think that's okay, or that. Okay, so moving, we're just going to kind of get more complicated as we go. That didn't require the chain rule, the product rule, or the quotient rule. We could have done the quotient rule, but it's a lot easier without it. So now let's take a look at one. Oh, we'll jump right into it. So this one, not only do we have to find the derivative, but we have to figure out where the horizontal tangent is. So that means taking the derivative and setting it to 0. Okay, anytime there's a horizontal tangent would happen when the derivative equals 0. That you have a tangent line with slope of 0. Okay, so that'll be our process. Take the derivative of this function. So let's see. I guess first we might want to rewrite it like this. All right, square root is 1/2, and then we'll go ahead and take the derivative over here. Low d high. Low denominator. D high derivative of the numerator minus high the numerator. D low derivative of the denominator. Let's see if I got enough room here. Derivative of the denominator is going to go like this. I need the chain rule. 1/2 2x minus 1, take away a half, negative 1/2, and then multiply by the derivative of the input function. The derivative of 2x minus 1 is 2. Sorry, that's so small, but the derivative of the denominator is that thing. 1/2, 2x minus 1 to the negative 1/2, that's a negative, times 2, using the chain rule. Okay, all over the denominator squared. If I square a square root, I just get that. Okay, calculus is done. Now for the algebra piece. Well, I could at least do that pretty easily. 1/2 times 2 is 1, so that goes away. That's going to be a plus. That was easy. And now generally, you see these are pretty common problems in Calc 1 that we want to factor something out here, right? So what I'm going to factor out, we can see that we have this expression, the 2x minus 1. Right? That's common. It's here and it's here. They have different powers, but we know how to factor. So I'm going to go ahead and factor that out. And in general, we like to factor out the power that's the lowest. And I'll show you why that works nicely for us here. Is there anything else common? I got a 6 and a 6. I can factor out the negative 6. So let's do that. Squeeze him in. Negative 6 times 2x minus 1 to the negative 1/2. Okay, so here's the question. 2x minus 1 to the negative 1/2 times 2x minus 1 to what power will give me 2x minus 1 to the positive 1/2? Well, that should be 1. So that makes sense. If you remember your exponent rules, if that's the first power, then since these are the same base, negative 1 and 1 is 1/2. So that should work, and that works nicely for us because 2x minus 1 to the first, well, to the first power, we can just work with 2x minus 1. There's no operation on it. We factored out a negative 6. That means I have to bring a negative back in order for it to be positive if I were to distribute. That x is still there. Oh, and now, I know you can't really see it, but that should be negative. We factored out 2x minus 1 to the negative 1/2. So that means there's nothing else to factor out. You could put a 1 there, but we don't really need it. Okay, so we are done factoring, and this one's cleaned up pretty nicely. On the bottom, I still got a 2x minus 1. So let me explain one more time why that works. If you were to check your work and distribute, go ahead and run this through. If you multiply this by this, 2x minus 1 to the negative 1/2 times 2x minus 1 to the 1 is 2x minus 1 to the 1/2, right? Because you'd add those two exponents. And that negative 6 would be here. Then distribute this. Distribute this here, and do you get this expression? Well, 2x minus 1 to the negative 1/2, if you ran it through, that'd be this guy, check. And then you just need a plus 6x. Negative 6 times negative x is plus 6x. So that's a little check. We know we're right. We've factored correctly. And now we're at least almost done with a nice looking derivative. Negative 6, this is going to go down. 2x minus 1 to the 1/2 times 2x minus 1 is 2x minus 1 to the 3/2. And then this cleans up real nicely. 2x minus 1 minus x is x minus 1. Okay, now we can answer the question. Where does it have a horizontal tangent line? Well, it has a horizontal tangent line when the derivative, when f prime of x equals 0. So if we set our derivative to 0, let's just go ahead and do that right here. then we can see that there's a solution at x equals 1. Right? That's our answer. When you set a rational function or something that looks like this to 0, you can set the numerator to 0 because 0 divided by whatever this is 0 as long as your solution is in the domain. Right? So if I go like that, pretty easily you can see that it happens at x equals 1. And that's in the only issue with our domain would be at would be what? Would be, well, it can't be a half, right? I guess we would be worried about where this is negative too, right? Where that comes from the function itself. But we don't have to worry about that because x equals 1. The function's defined there. The derivative's defined there, so we're good. Determine the points. Okay, so we're not quite done. It happens when x equals 1. So to find the y value, we plug in 1 to the function. Be careful, right? We're looking for the point. So a lot of times in Calc 1, we plug in values to the function and the derivative. In this case, we're plugging into the function because it's asking for the point. We use calculus to find where you have a horizontal. Now just to find a point on the graph, that's pretty easy. That should just be 1. And then our answer should be this guy. Okay, that's part 1 of my derivative review.